So today I'm going to go and solve this exam. It is October, November 2023. You can see the paper, right?
Yes, I can.
Okay, sure. Okay, so let us get going. Now for the question number 1. In this experiment, you will investigate the oscillation of a pendulum. So do you know what is the meaning of an oscillation?
Yes.
Periodic motion, right? Periodic motion of a pendulum. Okay. So now he's telling us set up the apparatus as shown. We got a stand, or we got a clamp, we got a piece of string with a putty or kind of a weight. Okay, and this is our spring. This is this is our pendulum. So, and he told us that the length L of the pendulum is the distance between the bottom of the wooden block and the center of the adhesive putty. So he told us this is the length L. Sorry. This is the length L, okay, of the pendulum. Remember, this is the practical question. You are going to carry out this investigation yourself in the exam, okay, and you are going to use a meter ruler to take this measurement. Okay. He told us adjust the center of the string so that L is approximately 53 centimeter. Adjust L to be approximately 53 centimeter. Okay. So what you are going to do, you are going to try to fix or to adjust this length. Okay. You increase it, you decrease it as needed so that it is approximately 53 centimeters. Okay. Now, as usual, whenever we get this type of question, we take two measurements for the value he asked us. We take two measurements for what? For the value or the quantity he asked for. Okay, so you took two measurements. You get the first one as 53.3. The second one is 52.7. Okay? So which value are going to use?
I will take the average.
The average as usual. Okay? So it is 53.3 plus 52.7
divide by
divide 2. We get 53.0 centimeters. Okay, this is good. So he now is telling us use the second boss to adjust. This is what is called the boss. It is a piece of metal or plastic or whatever. You can fix it on the stand, okay, and you can use it to attach some other components, okay. It is going to be something like a piece of plastic or something like this. Use the second boss to attach the wooden rod to the stand. Adjust the apparatus until the vertical string of the pendulum just touches against the wooden rod as shown in the figure, so and so. So we have, this is our pendulum. We are going to have this wooden piece, okay, or this wooden rod attached to the post, and we are just going to move it, okay, slowly till it just touches the string. Okay. It is very important in this paper to follow his recommendations, okay, or to follow very closely the instructions. You need to be very careful with this paper. So he is telling us the distance between the bottom of the wooden block and the center of the wooden rod is S. Now he's telling us where is S? This is S. Adjust the position of the wooden rod so that S is approximately 36 centimeter. Okay, so we adjusted approximately 36 centimeter. We carried the measurement twice, okay, and we used the average value. Okay, so what is going to be this average value? 35.9 plus 35.7 divide 2. Let us do this calculation. So it is 35.9 plus 35.7, and we divide by 2. It is 35.8. 0.8 centimeters. Okay? Now, calculate L minus S. We have L, which is 53, minus S, which is 35.8. Okay, what is going to be?
-8.
No.
-0.8.
No, 53 minus 35.8. 53 minus 35.8. It's going to be 17.2.
17.2.
17.2 centimeters. Okay. I just need to check something. Okay. Now he's telling us move the adhesive putty a small distance so that string moves away from the wooden rod. Release the adhesive putty. The string hits the rod as the pendulum oscillates. So can you imagine what we are doing? Can you imagine that?
No.
So now we have this piece of string. Okay, it is barely touching this piece of wood. Okay, so what we are going to do is move this a little bit away from the from this wooden piece. We move it a little bit, then we release it. What is going to happen?
It starts to oscillate.
It is going to move, right? So as it moves backward, the string, okay, is going to hit this wooden block or this wooden piece at this point, right? And we are going to see
Yes.
some kind of oscillation motion or a periodic motion. So this is what we expect to see. Now, take measurement to determine the period T of oscillations. And this is important. He asks us to determine or measure the distance, the periodic time or the period T of the oscillation. So, which instrument you are going to use for this? So, Dean, which instrument you are going to use to measure the periodic time?
The clock?
A stopwatch. It is a stopwatch. This is not a clock. Okay, we say it's stopwatch. Okay, so
Okay.
what we are going to do?
I will find the average.
It's not kind of finding the average. It is one way of saying it, finding the average. But what we are going to do, we are going to time at least 10 oscillations. We are going to time what? At least
10 oscillations.
10 oscillations. Okay? Why do we do that? If we try to time one oscillation, it is going to be very short and very quick. It's going to be very short and very quick. Okay? Then the error in measuring one oscillation, or the absolute error, is going to, the percentage error in one oscillation is going to be very big. So the way to go through it is to time more than one oscillation. Typically, we do 10. Okay? Typically, we do what? 10 oscillation. Why do we do 10 oscillation? To reduce the percentage error. Okay? So if he tell you, why do you do 10 oscillation? Nadim.
Yes.
So if he asks you, why do we do 10 oscillations?
To reduce the percentage uncertainty.
Yes, to reduce the percentage uncertainty. Okay, so we do 10 oscillations. For example, we get 24 seconds, 25 seconds, 26 seconds. So the time for 10 oscillations is 25 seconds. Okay, the time for one oscillation is 25 divide 10. 20.5 seconds. Is that okay? So far,
Mr.
so
Shaw,
good?
you added them?
Sorry? Yes, I'm going to
add-
calculate the average.
Okay, yes.
So this is the average, right?
Yes.
24 plus 26 divide 2, I get 25. And then I divide by 10. I get 2.5 seconds for one oscillation. We don't want the timing for 10 oscillations. We need one. But we did 10 to reduce the percentage uncertainty. Okay. Change S in the range S between 5 centimeters and 45 centimeters by adjusting the position of the wooden rod. Determine T. Repeat until you have 6 sets of values of S and T. Record your table results in a table. Include values of L minus S square root. Okay. So what we are going to do next, we are going to change the position of this rod, okay, such that S is between 5 centimeter and less or equal 45 centimeter as recommended. We are going to get 6 sets of values. 6 sets of value. Each time we are going to let the pendulum oscillate 10 oscillations. We calculate the periodic time. Okay? Is it fine with
Okay.
you? Okay.
Yes.
So this is our set of readings for this experiment. We tried for S in centimeters. It is important to put the unit on your table. Okay? Very important. So we tried with S equal 13 centimeter. We got the time for 10 periods or 10 oscillations at 14.9. 15 we got 14.7, 20 14.3, 36 12.9, 40 12.2, 45 11.4. So these are our readings. Now he is asking us to do what? To calculate L minus S under the square root, right? What is the unit?
Yes. Centimeter.
Not centimeter. Try again. Can you try
Okay,
again?
what is the unit of L?
Sorry?
What is the unit of L?
It is centimeters. And S is in centimeters. So the unit for L minus S is centimeters, right?
Yes.
Okay, but if we take the square root,
Centimeter under the square root.
yes, it is centimeter half. Okay, this is how we write it. Centimeter 1/2. Okay, now we just go and read a little bit. Plot a graph of t on the y-axis against L minus S on the x-axis. So to complete our table, we need to calculate the periodic time, t, right?
Yes.
T is simply t of 10 oscillations divide 10. What are the units here?
Second.
Second, right? So let us do the mass for it. Remember, L is 53, right? We had it here. This is L. So L is 53. And it is always going to be 53. So for the first one, it is 53, or let us say square root 53 minus 13. It is 6.32. 6.32. Okay, Dean?
Yes.
Okay, good. What about the second one? Second one is going to be square root 53 minus 15.
Minus 15.
Okay, so we get 6.16444, something like this. Okay? So how much do we report for it?
3 significant figure.
3 significant figures. 6.14, right? So why did we report it as 3 significant figures? Do you remember that?
Yes, because this is the smallest one.
Okay, because L and S are also reported in 3 significant figures, right?
Yes.
Okay, L and S are reported to 3 significant figures. Okay, let us do the rest. I think we got 5.7. Let me write what I have. 4.10, 3.60, 2.82. Okay, for the time it is going to be 1.49, 1.47, 1.43, 1.29, 1.20, 1.14. Okay, these are the values. Now we come to the important piece, or the little bit tricky one. What are we going to plot on the x-axis? Which value are going to put it on the x-axis?
The square root L minus S.
L minus S is going to be on the x-axis. So just to make life easy, let us say this is x-axis. And we write above here y-axis. Okay. Now, we go to the graph paper. We do count the number of squares. So we have 1, 2, 3, 4, 5, 6, 7, 8 on the x-axis. What are we plotting over here? L minus S, square root centimeter half. Okay. What about the y-axis? Let us do the counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? So we have 8 squares on the x-axis, 12 square on the y-axis. Okay? What are we plotting on the y-axis? It is t. And the unit is in second. Okay. Now, let us work out our way to the scale. The first question to ask yourself, okay? Now, what is the minimum here in this axis? Minimum is 2.82.
2.
What is the maximum? 6.32. 6.32. What if I decide to
Mister,
start? Sorry?
sorry بس أنت عامل zoom can you عشان I can't see it.
You cannot see the page now or what?
I can see the page but your zoom you make zoom in.
Sorry?
عملت zoom ف
I am zooming it in my page, or is it?
in your page.
Do you need to get it smaller or what?
Yes, please.
Okay, let me see. Is it like this or what?
Okay, كده yes, I can see it right now clear.
Okay. So what is the minimum?
2.82.
2.82. What is the maximum?
6.32.
6.32. Okay. Let us take our time today for the graph plot. Okay. So what we have is something like this. Okay. So the first question we can ask ourselves, what if we start the x-axis here from 0? What if we start the x-axis right from the beginning, from 0, and we end up in something like 6.3? What is the scale do we need for that?
1.
Okay. No, let us go easy.
Okay.
Okay. So if we say that 6.32, we divide by what? By 8, the number of squares in the x-axis. So it is going to be 6.32 divide 8. It is going to give us 0.79. 0.79. What is the next good scale?
8.
No, we round it up a little bit. We round it up to 1. We typically don't like scales like 0.8, 0.7, 0.6. Okay? We always prefer to got something like multiples of 1, multiples of 2, multiples of 5. Those are always the best to choose. Okay? So we round it up to 1. Okay? So let us go and see. So we have, this is 0, right? Can you see it? Can you see it, Deem?
Yes, I can.
Okay. So this is going to be 1, 2, 3, 4, 5, 6, and 7. So remember what are the values we have for the x-axis? 2.82 and 6.3. So where 2.82? There's something like here, right?
Yes.
Okay. And where is 6.3? There's something like here. Right?
Yes.
So if we make our graph plot, it is only going to be something like this. Or something like, I don't know. Let us say something like this. It is going to be very short on the x-axis. It is going to be very short on the x-axis. The whole of this area is not used. The whole of this area is also not used. We are only using what? 1, 2, 3 squares. 3 squares out of how many squares?
8.
3 out of 8. This is not a good scale. This is not a good scale. A good scale in our case, you should cover something like in the x-axis from 5, at least 5 squares. At least what?
5 squares.
At least. Okay? If they are 6, they are fine. If they are 7, it is even better. Can you see how we are working, Deem?
Yes.
Okay. The more you practice, then you can decide those things on the fly. You don't have to do the whole calculation. But I'm just trying to show you how you are going to think over the problem. Now, so I decide that I'm not going to start my x-axis from 0. This, what I came up to. I'm not going to start my x-axis from 0. So what I'm going to do? I need to start it from something close to 2.8 and end it close to 6.3. So this is how I do it. 6.32 minus 2.82. This is how I'm going to decide my scale. The maximum minus the minimum. I divide by how much?
By 8.
By 8, exactly. Now let me do the math. 6.32 minus 2.82 divide 8. I'm getting what? 0.437. 0.437. Okay? I don't go below this value. I always go higher. I always try to go up. Okay? So, what is the next best value I can choose? What is the next best value you can choose, Deem?
0.5.
0.5. 0.5. Okay. So, I'm going to start from a scale of 0.5, and I don't have to start from 0. Okay? Now, I'm not starting from 0. I'm going to start from something a little bit less than 2.82. The best to go is to start from 2.5. The other is going to be 3. What is the next one?
3.5.
3.5. The next?
4.
4.5.
5.
5.
5.5.
5.
6.
6.
6.5.
6.5. So we are going to get our values something like in this area. So we are good in the x-axis. We are good in the x-axis. Okay. What about the y-axis? How do you think we can proceed with the y-axis?
We can
Where's
subtract the maximum from the minimum, divide by
no?
12.
We have to go and ask ourselves first: is it worse to start from 0 or not? This is the first question we have to answer. Is it worse? What do you
We
think?
can try first. I think
We can
yes.
try first, right?
Yes.
Okay. So we are going to say what? 1.49. This is the maximum. We divide by 12. 1.49 divide by 12. Okay. It is going to be 0.12. 0.12. So the next best one is 0.2, right?
Yes.
Okay. 0.2. Okay. So it is going to be 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8. This is 1.49 divide 12. Okay. Okay. So if we do it like this, and we have our scale starting from 1.14 and ending up in 1.49. So from where it is going to be? Something from here to around here, right?
Yes.
So this is not quite a good scale. It is going to be very small. So it is not worth to start the y-axis also from the 0. Okay? We are not going to start
Okay.
the y-axis from 0. Okay. Then how we can calculate the scale?
The maximum minus the minimum, divide
Okay.
12.
Divide by what?
12.
Okay. So what are we getting? Something like 0.03. 0.03. Well, on a personal level, I don't prefer using things like 0.03, 0.04. They are not quite good while we are going to count the small squares. So what do you think is the second best one we can choose?
0.02.
No, we always go for higher.
0.05.
0.05. This is my personal choice. It's going to be 0.05. So I'm not starting from 0. I'm going to start from a value which is very close to 1.114. Okay? So the best one to go is 1.10. 1.10. Okay? What is going to be the next one?
1.15.
1.15. 1.20.
1.25.
Yes.
1.30. 1.35,
1.35,
1.40, 1.45,
1.45,
1.50.
1.50. We don't need to go further, right?
Yes.
Okay. So we almost have how many squares? 1, 2, 3, 4, 5, 6, 7, almost 9 squares we are going to use. Almost 9 squares we are going to use. So in the y-axis, in the y-axis, we need to use at least 7 squares. We need to use at least 7 squares. Okay?
Okay.
Okay. Now we go for how to present the data. Okay, let me make a copy of this. Let me clear it a little bit. So now we come to the how to represent the data. Okay, I think for this session, the time is going to go off. So we come back in 10 minutes, Deem, okay?
Okay.
Okay, we come back in 10 minutes. Okay, good. Let me grab my pen. Okay, so we now to go to this part where we are going to represent our data. Okay, so the first one, it is going to be on the x-axis. It is 6.32. And on the y-axis, it is going to be 1.49. So let us decide where it is going to be. So 6.32 and 1.49, it is going to be somewhere here, right? Oh, why are you doing this? It is going to be around here, right?
Yes.
Okay, so this is 6. Okay, and we have above 1.45. Okay, let us zoom in a little bit so we can. So this is, sorry, this is 6. This is 6. And this is 1.45. So for the x-axis, we would like to have 6.32. 6.32. So how do we do that? We say 6.32 minus, what is the scale mark which is closest to it?
6.
6. And what is the scale on the x-axis?
0.5.
0.5. Okay, do the math. Point 0.32 divide 0.5. So how many squares do we have? We get 0.64. Okay, so what we look for is this number. It tells us how many small squares we need to count from the 6 mark. Okay, how many small squares we need to count it from this mark. And what about 0.4 or this number? What do you think, Deem?
I think it is mean that it is between them, between
Between 6
the
and
6
7.
blank and the 7.
Okay, and then you can just decide. If it is something less than 5, then you put it closer to the 6. If it is 5 or more, you just put it closer to the 7. So let us start counting. This is line number 1, 2, 3, 4, 5, 6. And this is 7. So we are in between. So just let me mark it over here, just like this. Now we do it for the y-axis. How we are going to do it for the y-axis?
1 point.
Yes, 1.49
minus 1.45 divided by
Yes.
0.5.
No. It is not 0.5. Look at it again.
0.05.
0.05. Okay. Then 1.49 minus 1.45 divide 0.05. We get how many squares? 8, right?
Yes.
Okay. Then we start counting. This is 1, this is 2, 3, 4, 5, 6, 7, 8. And this is what we are looking for. This is the point we are looking for. Sure, we don't need to keep all this over here, right? Can you see how we are doing it? Is it okay with you, Deem? Deem?
Yes, it is.
It is, okay. Now we go for the second one. 6.14, 1.47. Again, 6.14. What is closest to it is 6, and we divide by 0.5. 6.14 minus 6 divided by 0.5. 0.28. So it is 2 squares and almost the third one.
Yes.
Okay, and we have 1.47. Again, somewhere here. So 6, this is 6, this is 1, this is 2, almost here. Okay, What about 1.47? 1.47 minus 1.45, and I divide by 0.05. 1.47 minus 1.45 divided by 0.05. 0.4, meaning 4 small squares up. So it is 1, 2, 3, 4. So it is around here. Okay?
Okay.
Now let us see. We are done with 2 of them. We have 1.43. Sorry, 5.7. 5.5, 5.6, 5.7. This I can do it easily, 5.7. And 1.43. So this is 5, right? 5.75. This is 5.7 over here. 1.43, 41. This is it. That one was easy. Okay, I did with the counting small lines. Okay, but we can do it again as we did before. So 5.7 minus 5.5, right? And divide
Yes.
by 0.5. So it is 0.2 divide 0.5, 4 small squares. So 1, 2, 3, 4. Okay, here is 4. What about the x-axis? It is 1.43 minus 1.4 divided by 0.05. 6 small squares. So we count from here. This is 1, 2, 3, 4, 5. This is the 6. So you don't have to do it this way. Okay, you can develop your own style. Now, 1.29, 4.10. Where is 4.10? 4.1 is somewhere here. And 1.29, we are around here. So 4.1, this is 4, right? 4.05, 4.1. This line is 4.1. And we have 1.29. 1.29. Okay. What about 1.29? I think 1.29 is here. So we are done with this one. Let me check something. Okay, this one is a little bit off. It is 1.22. I don't remember it. Okay. Are you following them?
Yes, I am.
Okay. Now we go for this one. This 3.60 and 1.22. So 3.5, right? This is 3.5. 3.55. This is 3.60. And about 1.2. 1.25. No, 1.205. 1.21. 1.215. 1.2.
2.
2. It
Yes.
is here. Okay, it is around here. So it is here. Okay. Now we go for the last one. 1.14, 2.82, and 2.14. So this is 2.8. And this is 2.85. So it is in between, right? Something like here. And we have 1.14. So 1.14 is here. Can you see it?
Yes.
Okay. Let us check if we did this one right. So it is 2.82. The closest to it is 2.5. And we divide by 0.5. 2.82 minus 2.5 divide by 0.5. 0.64. Oh, I'm overshooting it. 2.82. Okay. I'm counting this way. Minus 2.5 divide 0.5. 0.64. Yes, okay. 0.5, 0.6 around here. Okay, very good. For the y-axis, it is 1 point. For the yes, 1.14 minus 1.1 divide 0.05. 8 squares. 1, 2, 3, 4, 5, 6, 7, 8. We are good. Okay. Are we finding?
Yes.
Okay. Now we go for calculating the slope. Or, sorry, drawing the straight line. You have to use your meter ruler. It needs to be transparent. Okay? I'm not quite sure how I can show it over here for you. But so you have to use your meter ruler. Okay? And you need to make sure that you can pass through as many as possible points as you could. Okay, Dim?
Okay.
Can you see this line that I'm moving?
Yes, I can.
Okay. Then I try to, with my meter ruler or with my ruler, I try to go through as many as possible, as many points as possible. Okay?
Okay.
Like this. I don't have to go through the origin. This straight line doesn't go through the origin, because I noticed in the homework that you are sometimes forcing your line to go through the origin. It doesn't have. I need to follow the points. I need to follow the points. So how many points did I go through? 1, 2, 3, 4, 5. I have one which is a little bit far away. Can you see it?
Yes.
This one is a little bit off. Okay. What does it mean? If it is a little bit off?
Error.
Yes, I was not just careful enough when I was taking my readings. What should I do? Nothing. Actually, nothing. If it is just 1 point, okay, it is fine. Even if there are 2 of them, maybe you can see another one which is around here. Maybe. Then you have 2 which are a little bit off out of the 6. Then you are just fine. They don't have to be very far away, okay? Far away means that you have done a careless job. But if they are close enough, then it is fine. I need to do what? My line need to pass as many points as possible. Okay?
Okay.
Okay. Now we go for the gradient. Now we go for the gradient. So what are we going to do for the gradient? What do you think we should do for the gradient, Dean?
We'll just do like a triangle.
Right angle. Right angle, triangle, right?
Yes.
Okay. So this is the best thing, that your triangle should cover more than half of the line. Okay? It should cover more than half of the line. So what I'm going to do is delta x, or the change in x, delta y, divide delta x. The change in y divides the change in x. So what we got here is this. Gradient is 1.46 minus 1.15 divide 6 minus 2.9. These are the values I got from here and here and this one. This is how I calculate the gradient. I think you know how to calculate the gradient, right?
Yes, I do.
Yes, okay. So this is my calculation for the gradient. Let me clear this off. So gradient is equal 1.46 minus 1.15, 6.0 minus 2.9. If I do the math, let me check it. 1.46 minus 1.15 divide 6 minus 2.9. It is 0.1. 0.1. This is the gradient. Now I need to check for what?
Intercept.
No. Before that,
The unit.
the units. Okay. So the units are the units of y divided by the unit of x. What are the units of y?
Second.
Second. What are the units of x?
1 centimeter, 1/2.
Centimeter to the power of half. So this is my gradient. 0.1 second centimeter half. Okay. Now I need to do the intercept. I need to do the intercept. So how are we going to find the intercept, Dean?
First, see if it starts from 0 or not.
Okay. The x-axis, if it starts from 0.
It doesn't.
Right? It doesn't. So we cannot read it directly from the graph plot. We need to do some more calculation. So we are going to pick one point. The point I used okay, it is something like I pick any point from around the line. The point I used is somewhere here. Okay, I use 5.4 on the x-axis and 1.4 on the y-axis. I got the point over here. Okay, I use the point along the line. What is my point? 1.4 and 5.4 on the x-axis. Okay, 5.4 or 1.4. Now, what I'm going to do is write the equation of a straight line. Y is equal mx plus c. I'm looking at calculating c, right? So c is equal y minus mx. What is y for now?
1.4.
1.4. What is the gradient?
0.1.
0.1. What is the x?
5.4.
Yes, exactly. Do the math. 1.4 minus 0.54. Sorry, 1.4. 1.4 minus 0.54. 0.86. Okay. Are we done with the intercept?
No, we have to find the unit.
So we have to find the units. So what is the units for the intercept?
Second.
Yes, it is second. It is always the units of the y-axis. Okay?
Yes.
It is always going to be the same units as the y-axis. Okay. We are good here. Now he is telling us, go further. We are done with this part. It is suggested that the quantities T, L, and S are related by the equation. Okay, he gave us an equation where A and B are constant. Using your answer from before, determine the values of A and B. Give appropriate units. So how do we do that, Dean?
We can make A the subject of formula.
Sorry?
We can make A the subject of formula.
No, this is not how we do that. Think again. What was our plot of T and L minus S? Or square root of L minus S? What did we get when we plot T and square root of L minus S?
Do you mean the gradient?
Yes, when we make a plot, when we made this plot, T and L minus S, we got a straight line, right?
Yes.
Then T and this value are related as an equation of a straight line. Then we write here and we compare this equation to that of a straight line. T is
Okay.
equal A L minus S plus B. This part is always going to be how to compare this equation, an equation with an equation of a straight line. Y is equal M, this is X plus C. So the dependent variable was T. L minus S is the independent variable. So what is A and B?
A is the gradient, B is
Okay.
the y-intercept.
Is the y-intercept. So A is the gradient, B is the y-intercept. So he told us calculate value determines the values of A and B. Then it are just the gradient and the y-intercept, right? 0.1
Yes.
second centimeter to the power half. 0.86 seconds. Are we good?
Yes.
Okay. He is telling us theory suggests that A is pi over square root of g, where g is the acceleration of free fall. Use your answer in so and so to determine a value for g. Give an appropriate unit. Okay? So he gave us a relation between the gradient, which is A, and the acceleration due to gravity. And he is asking us to calculate g, right?
Yes.
Okay. So from this equation, can we write it for g?
Yes.
Okay.
G square equal pi over A.
G square?
G and G under square root
G under square root is equal
equal pi over A.
over A. So what about g itself?
I will square G.
You will square both sides, right?
Yes.
So g is equal pi over A all square.
Square.
Okay. Do we know pi?
Yes.
3.14. Do we know A?
0.1.
0.1. All square. So 3.14 divide 0.1. Okay. And then we square the answer. 985.96. Point, how much?
9.96.
Okay. Is that good?
Then the unit is second minus 1.
Sorry?
I will find the unit.
And what is the unit for G?
A second minus 1.
No. G, what is G?
The G is free fall meter per second square.
Meter per second square. Do you know what is the value of G?
Yes, I do.
How much?
9.81.
9.81 meter per second square. But what are we getting here?
985.96.
So does it look right?
No, it doesn't.
And what is the problem? Are we doing something wrong? Are we okay? What do you think?
Maybe it is the acceleration of free fall of another planet.
No, he's not telling us. This is, remember, this is an experiment that you carried in the lab, right?
Yes.
Okay, so what do you think? Can you tell me the units over here on this G that we calculated?
What?
Can you tell me the units that we have over here?
Okay. A, it is second.
Sorry?
A is second.
A is second. No, A is not second. A is second divided by centimeter half.
Okay.
Okay. Then what do you expect the units here is going to be?
Yeah, because in G it is meter per second, and we have centimeter.
We have centimeter per second. Centimeter per second square, right? So we need to change this value to meter per second, right?
Yes.
Okay, what are we going to do? When we are going from centimeter to meters,
We divide
we divide
by
by how much?
100.
By 100. Okay, so we divide this by 100. So it is going to be 9.8596 meter per second square, right?
Yes.
Okay. Are we going to report everything?
No.
We are not going to report the whole thing. What we are going to keep is only two significant figures. I will keep only two significant figures. Okay? So it is going to be something like 9.9 meter per second square. Okay?
Okay.
Do you think we are fine?
Yes.
Do you have any questions over here?
No.
Okay. Now we go to the next question. In this experiment, you will investigate a wooden strip resting at an angle. You are provided with a wooden strip as shown. So we have this wooden strip. Okay? The dimension of the strip are x, y, and z. So he's telling us what are the dimensions. X, y, and z. Measure and record x, y, and z. X and y and z. So how are you going to proceed with that if you are giving this in the lab?
For X, I can use a measuring tape.
Or a meter ruler, right? Usually, we
Yes.
typically use a meter ruler. Okay. Okay.
Okay.
And then it depends about y and z. If we have a vernier available, then we can use a vernier, right?
Right.
And if it is not just small, okay, the width or the height of the wooden ruler, if it is small, then we can use a vernier if it is available. If not available, then we can go again with the meter ruler, right?
Right.
What else we should do?
We should take the reading twice so we can get
Yes,
the average.
yes. We are going to take two measurements for each value. Two measurements for x, two measurements for y, two measurements for z. Okay? and we are going to calculate the average value. So I assume that I did that, or we did that. We got 0.513, 0.021 for y, and for z we got 0.012. Now, the volume of the strip is given by x times y times z, right? Calculate the volume. What are we going to do?
I will multiply 0.513, multiply 0.021, multiply 0.012.
Okay, then we do this math. Okay, I did that and I got 12.9 10 to the power minus 5. Okay?
Okay.
Okay. Sorry, 12.9. Now, justify the number of significant figures that you have given for your value of V. Okay, I kept 3 significant figures. So this is important, Dean. If we look at this, we have X. How many significant figures do we have?
3,
3. For Y?
3.
No.
It is 2 for y.
2 for Y. And what about Z?
2.
2. So we either keep 2 significant figures, or it is also acceptable if we keep 1 extra significant figure. So if the smallest, the one with the least significant figures is 2, right? So we can keep our value to 2 significant figures. This should be fine and okay. Or we can give it 1 extra significant figure, as I did here. We used 3 significant. So let us get going. So we stopped over here. So we need to justify why did we use 3 significant figures or 2 significant figures, as you decide yourself. We used 3 significant figures to be compatible with the number of significant figures in X, Y, and Z. This is how you typically answer this part. Now, let us proceed further. Okay. Set up the apparatus as shown. So he's telling us to set up the apparatus as shown. We have a stand, we have a boss, and we are lifting the piece of wood as shown in the figure. Can you see the figure?
Yes.
Okay. I don't know why it is not going. Okay. He's telling us adjust the position of the boss so that the rod of the clamp is approximately 0.3 centimeter or 0.30 centimeter or 0.3 meters above the bench. Okay. He's telling us to set this height to 30 centimeters. Use some adhesive putty to secure the 30 centimeter ruler to the bench as shown in figure 2.2. So we are putting a putty over here, okay, to make sure that this piece of wood doesn't slide. The raised end of the wooden strip is R. The raised end of, okay, here is R. As shown, place the wooden strip on the rod and adjust the position of the stand so that the distance between the rod and R is approximately 5 centimeters. So we are going to set up this experiment, the setup as instructed. We just here need to follow his instructions. We don't have to do anything more. Use adhesive putty to attach the mass to the wooden strip so that the distance d between the lower end of the wooden strip and the center of mass is approximately 0.15 centimeter or 15 centimeters. So we have a mass. We are going to attach it to the putty. Okay. Okay. And it is going to be approximately 15 centimeter from the end of the piece of wood. Measure and record D. So we are going to get two values for this distance D. And we are going to calculate the average. What we get is this value. Are you following them?
Yes, I am.
Okay. Now use adhesive putty to attach the loop of string at the raised end of the wooden strip as shown. So we have a Newton, we have an adhesive putty somewhere. We are attaching it at the side of the wooden strip. Use a Newton meter to determine the vertical force F needed to just lift the wooden strip from the rod. So do you know what is a Newton meter?
Yes.
Okay. We use it to measure forces. We use it to measure what? Force. That is why it is called a Newton meter. So what is he telling us? That we attach a Newton meter, okay, at a point over here, and then we slowly lift up. We slowly lift the piece of wood, and we take a reading on the force meter or on the Newton meter when the wooden strip just leaves the boss. Can you imagine that?
Tell us, leave the what?
Sorry? Just, okay. So we have this setup. Can you understand this setup?
Yes.
Okay. So we have this piece of wood.
Yes.
It is standing on this this post, right? It is keeping it from falling. Okay?
Okay.
So we start lifting or pulling up slowly and gently through the Newton meter till we are just till the piece of wood is just leaving what? The boss. It is not anymore being held by the boss. Can you imagine that?
Yes.
So it is just lifting up. And we now take a value for F. As usual, we repeat this procedure 2 times, and we take 2 values for the force. We use the average. What is the average now? Can you see the average?
0.42.
No. What is point? Do you have your calculator around? It is 0.46.
Yes, I have it.
Okay, so you can calculate it. 0.48 plus 0.44 divide 2 It is 0.46 newtons. He is telling us estimate the percentage uncertainty in your value of F. Show your working. So, how can we calculate the percentage uncertainty? Do you remember how we calculate the percentage uncertainty?
Yes, it is the change. It is the uncertainty divided by the number multiply 100.
Yes, delta F divide F by 100. We know F, right? Is this average value? Do we know
Yes.
delta F?
No.
How can we calculate?
From the device uncertainty.
Well, you can use it from the device uncertainty if we are taking just one result, one reading. If we did the experiment once, okay, then yes, the uncertainty, we can get it from the instrument uncertainty, but we are carrying it twice. So it is going to be the maximum minus the average. Okay, maximum minus the average. What is the maximum for F? What is the maximum value for F, Dean? Can you hear me, Dean? Dean? So can you hear me? Dean?
Yes.
Can you hear me now?
Yes, I can.
Okay, so we said that if we are just doing one measurement for the force, yes, the uncertainty is going to be that of the instrument. But what if we have two? We can use maximum minus average. What is the maximum for F?
0.48.
0.48. What is the average?
0.46.
What is delta here? Right? So this is going to be 0.02 divide 0.46 multiply by 100. We get something like 4.3%. 4.3%. Okay. Now let us proceed further. Again, adjust the position of the mass so that D is approximately 30 centimeter. What is D? D is this, where we are placing the mass. So we are moving it a little bit higher. Instead of 15, it is going to be 30 centimeters. Okay? And we do need to do the whole thing again. We have to move or to try to lift the piece of wood a little bit or gently till it just above the boss. So we have again two values for D and we calculate the average. We have two values for F and we calculate the average. Okay? Are you following?
Yes.
Okay. Are we fine? Do you have any
Yes.
questions? Do you have any questions?
No, I don't.
Okay. So finally, we have two sets of values. Two values for F and D, and again, another set of values for F and D. It is suggested that the relation between F, X, and D is this relation, where W is the weight of the mass and has the value of 0.49 newtons. 0.49 newtons. So, and K is a constant. Using your data, calculate two values of K. So, what we are going to do, rewrite this equation, okay, for K. So, what is K is going to be equal?
Fx minus Wd.
Fx minus Wd. Okay, we have D is equal 0.4341 meters and F is equal 0.68 Newton. This is one set. Another set, D is equal D is 0.158 and F 0.46. 0.158 meter and F is equal 0.46 Newton. Is that okay?
Yes.
We have W is equal 0.49 newtons. So we just substitute. We simply substitute all these values in the equation and we calculate two values for K. So K1 is going to be 0.68 times X. Do we know X? Yes, we know X from before. 0.4513. So X equal 0.513 meters times 0.513 minus 0.49 times D 0.341. We do the math, we get 0.181. Okay? We do the math again for K2. It is going to be what is F 0.46 times what is K 0.513 minus 0.49 times 0.158. What we are going to get? 0.159. So we get 0.181 and again another value 0.159. Are we done with for the values of K?
Now we'll write the unit.
We write the unit. What do you think the units for K is going to be? What do you think? Can you think of a way that we can get the units for K?
I will write all of the units of the numbers that I have.
Okay. Can you do that? Can you tell me what you are going to get?
Okay. Okay. The first one is Newton a meter.
Okay.
Then also Newton meter. So
Yes.
Newton square meter square.
No. So if X equal WD plus K. So we know that if we have two values added together, we have two values or two quantities added together. Okay? They need to have the same units. Isn't it?
Yes.
We cannot add time with length, right? We can always
Yes.
add time with time, length with length. So if two values are added together, then they also have the same units. So K have the same units as WD. What is WD? As you said, it is Newton meters. Newton meters. Is it okay? Did you get it?
Yes.
Okay.
Yes.
Now, it is suggested that the percentage uncertainty in the value of K is 15%. Using this uncertainty, explain whether your result supports the relation in C or not. So, how do you think we can proceed? What do you think?
I will try it first.
Sorry?
I will find the percentage uncertainty of K first.
Yes, you are going to find the percentage uncertainty. So we need to calculate delta K, divide K by 100, right? So what is delta
Yes.
K in this case? Or what is K? First. What should we use for K?
The first value? No, the average.
The average. Okay. 0.159 plus 0.181 divide 2. We get 0.1695. Okay. We have here three significant figures. Then we are going to keep three significant figures. So K is equal 0.170 Newton meters. Is that okay?
Yes.
Now what about delta K?
Maximum minus average.
Minus average. So what is the maximum?
0.181.
170. 0.010. Okay? Newton meters. So we calculate delta K divide K by 100, which is 0.01 divide 0.170 times 100. We get something like 5.9%. So does it support our finding or not?
Yes.
Yes. Why?
Because it is smaller than it.
Smaller than what is expected for the values of k. Okay,
Yes.
then what we say, yes, our results support the assumption as the percentage uncertainty in k is approximately 6%, which is less than the allowed value in k. Okay? Is it clear?
Yes.
Okay. He's telling us now, theory suggests that k is equal rho v x over 2, where g is given and rho is the density of wood. Your second value is now telling us use our second value of k and values from a to determine rho. Give an appropriate unit. So we need to just rewrite this equation for rho. So what is rho going to equal?
2k
2k
over GVX.
g vx. Do we know everything? He instructed us to use the second value of k. Okay. Which is 0.159. So it is 2 times 0.159. Divide 9.8 times v, it is 0.15 times 10 to the power minus 5. We got this value from before. Okay, and what is x? 0.1, x is, v is 12.9, sorry. Times 10 to the power minus 5. What is x? It is 0.513. We do the math and we get something like 558.1 kilogram per meter cube. Okay, Dean?
Okay.
Can we do that? We have everything, right?
Yes.
0.159, we know it from the second value we calculated. G is given. We calculated volume before. And we know X. So everything in place. All the units are fine. The volume was in meter cube. X was in meter cube. G is in meter cube. Everything is fine. Just we plug in the values in calculator and we get the density. And we know the density is kilogram per meter cube. Okay?
Okay.
Then we are fine. Describe 4 sources of uncertainty or limitations of the procedure of this experiment. For any uncertainty in the measurement, you should state the quantity being measured and a reason for the uncertainty. Okay? This is a standard question. So, what do you think we should write that the first limitation?
We should write that taking only 2 measurements is not enough.
Taking 2 set of values is not enough. Okay? Okay. What else do you think? As I said, as you carry out the experiment yourself, you will see there is kind of some difficulties that you encounter. And you have to be a little bit open-minded and creative. So for me, I think one of the difficulties is when is telling you just the bar comes above the stand. It might be a little bit difficult to decide when does it exactly come above. Okay, then I can mention this. To decide when the bar lifts off from the boss. Okay. Another difficulty can be the difficulty of measuring accurately the distance d. Okay. We need
Mr.
to
Also, this one
what?
in the above experiment,
Yes.
there is, for example, there's a thing that prevents the wood from falling.
Sorry.
There is a thing that prevents the wood from falling down.
Yes.
It can slide.
No, you can see he's putting this piece of putty or sticky putty so that the slide the rod doesn't slide or the piece of wood doesn't slide.
Okay.
But if you think that it is going to slide, then you can mention that. Okay.
Okay.
Here the question is a little bit open. Okay.
Okay.
Difficulty to measure the length d due to difficulty to decide the center of the mass. Remember always when you are answering this part, okay, you are saying which value you have difficulty with measuring, okay, and why is that. Another difficulty might be difficulty to keep the Newton meter vertical while taking the reading. Okay. What about recommendation? So recommendation are always going to be, what should we recommend? Our solution to the above difficulties. Okay. Give me 5 minutes and I will be back. Okay. So what I'm saying that for the recommendation, okay, it is always going to be as a recommendation or solutions to what we found difficult in the first part. So the first one, what do you think the recommendation for the first one is going to be?
Take 6, 7, or 10 readings.
Okay. Take more sets of readings, at least 6 sets. Okay. When we have difficulty deciding when exactly the bar lifts from the boss, we can say that use video recording system to help take the readings more accurately. Okay. For the part 3, make sure that the readings for the mass edges on the bar average to 15 to D. Okay. Clamp the Newton meter using another to help keep it always vertical. Is that okay, Dean?
Yes.
Okay. So this is how we answer this part of the question. Do you have any questions for now?
No, thank you.
Okay. Then we are going